Okay, so in our final section of volume, we're going to be changing the game rules quite a bit here. So we're going to find a volume of a solid, but we're going to be using cross sections of popular geometrical shapes. So we're going to start with an example, and let's just see if we can paint a picture of what's happening here. Find the volume of the solid whose base is the area bounded by the graphs of y equals 6, x equals 2, x equals 0, y equals 4 times the natural log of 3 minus x, and whose cross sections are squares perpendicular to the x-axis. A little bit hard to visualize when it's in words like this. So let's start by making a two-dimensional graph of these functions. Y equals 6, there's your purple line. X equals 2, that's this brown vertical line. X equals 0. X equals 0 is the y-axis. And y equals 4 times the natural log of 3 minus x is this green function right here. Now it says the cross sections are squares perpendicular to the x-axis, which probably doesn't make much sense to you. So we got to look at this in a three-dimensional model. So here is the same graph, but in 3 dimensions. All right. Again, we got the purple line, y equals 6, coming up this way. All right, well, first of all, the green axis is your y-axis. The red is your x-axis. Purple is y equals 6. Brown, x equals 2. All right, and then 4 times the natural log of 3 minus x is this green function right here. And, of course, x equals 0. That's going to be your y-axis, which is lying down here. Now, if you imagine, we're going to be, it's hard to imagine, but we're going to be putting squares in this shape right here, in this area, bounded by these lines. But the squares are going to be perpendicular to the x-axis. That means the sides of the squares themselves are going to be perpendicular to this red x-axis right here. So what does that look like? Well, if we just put one square in there, this is what that one square is going to look like. It's going to come up off the paper. Now it's a square, so that every side of the square is exactly the same length. That's what a square is. And notice that the sides of the square and the x-axis form a perpendicular relationship. Okay. Now, we're not just doing one square. If we were, it would look like this, right? But we're doing many squares. And as I move that shape closer and closer to the y-axis here, to that green axis, we can see that the squares are going to get smaller and smaller. But remember that all sides of the square have exactly the same length. All right, now, well, that's like 6 squares right there, but we want infinitely many squares. So now it starts to take on a shape like this. All right, so there's the three-dimensional model. So hopefully it's starting to make a little bit more sense now. Of course, we're going to use an integral to do this, but we got to know the length of the base of the square. All right, so here's what we got. The length of the base of the square, if you can picture this, it's going to be the distance from the horizontal line y equals 6 to the actual function 4 times the natural log of 3 minus x. So that distance there is going to be 6 minus 4 natural log 3 minus x. That's the distance of one side of a square. And the squares are popping up off the paper at us, but we know that all sides of the square have the exact same length. The thickness of each square, since it's perpendicular to the x-axis, is going to be delta x. I don't know what the thickness is. It's probably going to be thin, but it's going to be some change in x, delta x. The volume of each square, all right, the volume is going to be the length of the side squared times dx. Remember, it's a volume. So this looks like a little, it's a square, I don't know what you want. It's a square with some sort of a thickness to it. So it's the length of the side of the square, but we're multiplying that dx times. All right, so there's the volume of each square. Well, how many squares do I have? I have infinitely many squares. And where do they reach to? Well, the squares go from x equals 0 to x equals 2. Where does the 2 come from? Well, the 2 comes from the fact that 4 times the natural log of 3 minus x is going to cross the x-axis down here at x equals 2. So this is our volume integral with cross sections of a square. Okay, and when we calculate that out, you get 26.266. Now, I think we're at a point now where we probably should get you more comfortable with your calculator to make sure that you know how to find these volumes. So in the activities that follow, not today, but in the future, in the activities that follow, we will have you be figuring out the actual volume. And that's how that works.